Okay, we have discussed about what is PCM in the previous video. So we can have a look at what is PCM in detail. Okay. In this video we will discuss about what is sampling, then quantization and encoding. These are the major steps that are taking place in PCM. Okay. First we have a look at block diagram of the PCM. Okay. I haven't included this block diagram in the previous video, as I think it is better to include this in this particular video. Okay, for the explanation it's better. For more detail about the introduction of the PCM, we can just refer the previous video. Okay. Students who are just looking this video will not get correct picture of the PCM. To get the correct picture, you have to just refer the previous video. Okay. For PCM to take place, there should be a continuous time message signal, and the continuous time message signal should be produced by a source. The source will produce a continuous time message signal, and this signal is passed through a low pass filter whose frequency should be FC, that's equal to FM. So we all know, we have studied in the previous semesters what is a low pass filter. Low pass filter will pass only low frequency components of a message signal. Am I right? Do you know what is the waveform of a low pass filter? Do you know? Yes, I will just draw it here. The waveform of a low pass filter will look like this. This drawing is not at all good, and this will be the point or cutoff frequency. Up to this point of frequency, all the signals will be passed. Okay, and after this frequency, no any frequency will be passed. This is what is low pass filter. Okay, then let's look at what is sampler. What is sampler? A sampler will produce sampled output. Am I right? The if an analog signal produced is like this, the sampled output will be like just lines. And the sampled output will be just lines. Am I right? The sampler will discretize the time. Okay, it's very difficult to draw using the mouse. Okay, this is the positive cycle, and this is sampled in the x-axis. Similarly, in y-axis also there will be sampling. Okay. This is analog signal that is passed, and this is after passing through the sampler we will get this type of waveform, that is, it is discretized. Then it is passed through quantizer. What happens in a quantizer is it will again discretize the amplitude of the wave. Okay, and then that is approximation. If this is particular signal is 1.8, it will be approximated to 2 maybe. Then if this signal is 2.6, it will be approximated to 3. Like that, for a particular signal whose amplitude is in point values or decimal values, it will be converted into an integer value. What does sampling means? Sampling means discretizing time, that is discretizing the x-axis, that is there will be only integers for each of the signal. Each signal there will be integer values. Similarly, in y-axis also, after quantizing we will get what? It will be discretized. Okay, this will be, if this is 1.2, this will be discretized to this particular value, and if this is 2.4, this will be discretized to 2. Okay, like this. If this will be this is 6.6, this will be discretized to 6 or 7. If it is discretized to 6, we can say that this is cut here. Like this, this will be approximated to a particular level. Okay, in the following slides we can see that in detail. This drawing is not much better. Then next step is encoding. What is encoding? Encoding means conversion of a signal that is coming from the quantizer into a binary form. So we will get output as 1, 0, 1, 1, like that. This is an example only, and there may be differences in the ones and zeros. A sequence of binary code will be produced, and the parallel to serial converter is placed at the last point of the block diagram, and this particular thing will do what? The parallel binary codes will be converted into serial manner. Okay, this is parallel, this is serial. Okay, this parallel codes will be converted to serial codes. Okay, am I clear? Okay, this is about the block diagram. If the block diagram is clear, then it will be very easy for you. Then this is sampling. As I have discussed earlier, this is analog signal. This is an analog signal, and this analog signal is getting sampled, and this type of discretized time waveform is produced. Okay, I think you got what is sampling. Then the output of the LPF is fed to a sampler where the analog input is sampled at regular intervals. We have said that the sampling of the signal is done at a rate of Fs. Okay, the sampling frequency is so selected that it must follow the sampling theorem. Okay, what is sampling theorem? The Fs must be greater than or equal to 2 Fm. This is the condition in sampling theorem. What is Fm and Fs? Fs is the sampling rate, and Fm is the maximum frequency component of the signal, input signal. The output of the sampler is a discrete continuous amplitude signal. Okay, am I clear? You can comment the doubts in the comment session so that I will clear the doubts. Okay, then quantization. As I have explained earlier, quantization means approximation of the amplitude to particular levels. Here this is approximated to 9. This is analog signal. Okay, and this is approximated to 9, then this 11, then this is in between this 12 and 13. It is approximated to 13. It is in between 13 and 14. It is approximated to 14. Between 15 and 14 there is no signals. All the signals, there are signals, analog signals are there. These are approximated to 15. So it is very easy. So, like that, all we can see in the negative cycle also. All are approximations. Approximations are done in order to discretize the amplitude. Okay. Okay. Then a quantizer is a unit that rounds off each sample to the nearest discrete level. Thus, quantizing a signal introduces some distortion or noise into it. This is known as quantization error. And there are two types of quantization errors. One is uniform and non-uniform. Okay. the uniform quantizer. Do you know what is uniform quantizer? In uniform quantizer, there exists a uniform spacing in between the levels. That means the step size will be equal for uniform quantizer. That is, spacing between two levels will be equal. But in the case of non-uniform quantizer, the spacing between the levels is not uniform. I will explain what is uniform quantizer and non-uniform quantizer as well as the step size in the next video, and there are some small derivations also. That part will discuss in the next video. Again, now this is okay. Then quantization error. As we have learned, what is quantization error? The quantizing a signal introduces some distortion or noise into it. Okay, this noise is known as, or distortion is known as, quantization error. This quantization error can be represented as epsilon, and this is the difference between input or sampled value and the quantized value. The sampled value minus quantized value gives us the value of quantization error. If sampled value is 5 and quantized value is 4, what will be the quantization error? 5 minus 4. Okay. If sampled value is say 8. Okay. Sampled value is 8 and quantized value is 10. Then what is the epsilon, that is the quantization error? It will be 2. How? Its magnitude is taken. 8 minus 10 equal to 2. Negative 2 will be coming and its magnitude is taken. Okay, am I clear? That is quantization error. Then quantization noise. What is quantization noise? Due to quantization error, this occurs. That is, due to quantization errors, we cannot get exact data or information. Am I right? Because actual information is lost and we get a distorted data or information at the receiver side. The distortion due to quantization error is known as quantization noise. There will be a quantization noise, and the quantization noise is only due to the distortion due to the quantization. Then encoding. What is encoding? Encoding is the process of conversion of the quantized signal into binary codes. This is the analog signal that we have transmitted, and this is converted into the sampled. It is sampled and it is quantized. After quantizing and sampling, we have converted it into binary forms by the process called encoding. We can arrange each voltage levels. There will be 0, 1, 2, 3, etc. and 0, minus 1, 2, 3, etc. from the below level to higher level, or we can take as we like. We are arranging them from 0 to up to what number we can take. That there is a formula relating to this that we'll be discussing in the next video. Now just introduction is there. So we will be converting each voltage level into a particular binary form, so that we will be easy to represent. And in the digital systems, digital networks, in order to transmit as digital in digital form, we have to use binary codes. That is why we have converted into binary codes. Then quantized signal is L level digital signal. There will be, consider we are having L levels. Okay, encoding converts L level digital signal to 2 level digital signal, that is binary signal, zeros and ones. then number of levels L will be less than or equal to 2 raised to n. What is n? N is the number of bits of encoding. If n equal to 2, that is number of bits are 2, what will be L? L will be less than or equal to 2 raised to 2, that is equal to what? 4. So we have to use number of levels. 4 levels can be represented using 2 bits. This is the bits. 2 bits. Okay, 2 bits we can use for representing 4 levels. Okay, this is representation of bits and this is the representation of levels. Okay, am I clear? Okay, this is a formula. There will be some numerical problems relating to this in your question paper, so just be aware of it. And here also we can see from 0 to some number, it have been quantized. It can be depending upon the user or the designer, that the number of bits and the levels will be there. Okay, then last step is parallel to serial converter. What is it? The data will be obtained in parallel form, that is encoded data will be in parallel form. This should be in serial form in order to transmit easily. So we are just arranging this in the serial form in order to get transmitted easily. Okay, this is about the encoding. Then coming to the transmission path, PCM has a transmission path. It has a transmitter, we know, and receiver. Between the transmitter and the receiver, there will be a transmission path. While going to the receiver, it will be distorted. The signal gets distorted. It will be noise. It will get noise and many problems will be there in the particular signal. For this, we are using regenerative repeater in between this particular transmitter as well as receiver. Regenerative repeaters have the ability to reshape or improve the distorted PCM signal, and they will restore the pulse. The pulse that is being transmitted from the transmitter will be reshaped and restored, amplified and transmitted with the same power and shape to the receiver with the help of regenerative repeaters. Okay. Then next part is the receiver, PCM receiver. Similar working of the transmitter is taking place here. Okay. Incoming PCM plus noise signal will be there, and this will be passed through the regenerator and we'll get a PCM. That here what happens is the signal gets decoded, encoded signal will get decoded, serial to parallel converter, again the data will be converted to parallel, and then digital data will be converted to analog signal, the previous signal that is transmitted. Okay, then by the help of the digital to analog converter as well as sampler, that signal will be restored and will be at last passed through the low pass filter, and we will get the original signal. The original signal will be reconstructed. The X of t will be getting the output. Okay, thank you. you can comment on the videos that you want for the doubt clarification, as well as if you request me to do more videos on the topics that you want to know on the electronics field, you can just comment on the comment box about the topic, and I'll be explaining the video in the next coming videos. Okay, so do subscribe the channel and just click on the bell button for the upcoming videos, and comment your opinion in the comment box. Okay, thank you.